Okay, so now we're going to start moving into the coding, and there's going to be two parts. There's going to be light and there's going to be nutrients. And we're first going to work on the light. And so we'll do the code for the light, and then so we'll stop and do the code for the light, and then we'll do the code for the nutrients. And so you read in the data, and then we start a for loop. And we have NT time steps in the for loop, and we keep going until we're finished. And then we're going to do calculations. And first, we're going to calculate the time in basically fraction of a day. And we're going to use the modulo symbol, which means you just get the remainder over 24. So like if you had 27, you were in time step 27, it would be 3. And that way we'll be able to go through each day and see what time of day we're at. Then we're going to use a sine curve based on that time of day in order to calculate the sunlight intensity at any time. And then we're going to calculate an effective sunlight, and that's going to be based on the concentration versus the maximum concentration. Then we're going to use a growth coefficient, conversion factor based on the light. So that's what we'll be working on this first time step. So in our algae model, which was developed by Dr. Michael Huesman at the Department of Energy, we divided the culture into 100 layers. And we calculated the penetration of light to each layer with a modified Beer-Lambert law approach, where Beer-Lambert law calculates the amount of light absorption by particles or cells. And so higher algae concentration reduces light penetration and thus results in lower average light for the culture as a whole. And then Dr. Huesman found that for a different kind of algae than we originally started with, the Beer-Lambert law wasn't working. And so he spent 6 months trying to figure out what was going on. He's a microbial engineer, with PhD microbial engineer. And he couldn't figure it out, but then he found this paper by this person in Korea, which discussed the shading of cells in the culture. And so it modifies the Beer-Lambert law. And then once he used this modified Beer-Lambert law, the model worked for all the types of algae that we had. So that was very impressive, I thought, that he did that. We calculated the algae growth every 5 minutes in each layer, each of the 100 layers. So we had a light intensity in each layer. And we calculated the growth coefficient based on the temperature of the culture and the light intensity in each layer. And the light intensity at the surface of the culture came from the weather station. But in this class, we're going to input a maximum light intensity. And I think in your spreadsheets, we said it was 800. And that's a typical maximum light intensity in Tucson, 800 watts per meter squared. And then we'll vary that light intensity with a sine curve. And so that's why we're doing this time of day calculation, where we take I minus 6, which is due to the fact that the sun rises at 6 a.m. and we want the sine curve to get above 0 right at 6 a.m. You know, obviously there's no light at midnight. So we take the I, which is the time step, minus 6, then modulo 24. So let's say we were at time step 36, as I've already said. Then we would be at what time of day with modulo 24 for time step 36? Each time step is an hour. That's a good question. And we specified the time steps as 0.041667, which is 1/24th of a day. That's what we specified our time steps in the,
Semester 36 time steps. How would they, what time is it?
what time of day is it?
You're starting at 0,
Yeah,
12. Like,
yeah, noon. And, but we're gonna offset that a little bit by I-6 because we want that would be the peak time of day according to the sine curve. The sine curve would rise and then you'd have that peak. And then it would go down and go negative and then come up again. And then the reason we're dividing by 24 is we're gonna use the number in the equation. And so I wanted to vary it between 0 and 1 instead of 0 and 24. I could have varied it between 0 and 24 here and just divided by 24. But I divided by 24 there. So we have time of day in decimals going from 0 to 1. Then we calculate our light intensity for the culture as I0 times NP dot sine. So that's a sine function. And then we have 2 times pi. And so we take the 0 to 1 and we convert it to 0 to 2 pi in order to get a sine curve. And so that'll give us our light intensity at any time. And then we're going to adjust, instead of using the Beer-Lambert law for 100 layers, we're going to make it a little simpler for this class. So we're going to adjust our concentration or our light intensity, and we're going to get the average light intensity for the culture. And so that's going to be some function of the light at the surface and then how much is being absorbed. And so we're going to use this simple equation where the effective light intensity is the I at the surface times the maximum concentration minus the concentration over the maximum concentration. So let's say the maximum concentration is 2 and the concentration is 0.5. We would have 0.5 over 2. So the effective light would be only 25% of the light that hits the outside of the algae culture. Then, and this is what we did with Dr. Huesman's work, and it wasn't as simple as just a growth coefficient times I effective. It was a curve, and actually it was many curves. We had, and I don't even remember how we did it, but we had 2 dimensions, light and temperature, and then we would, I think it was based on data tables. We would calculate the growth coefficient based on where it was in that light and temperature space. But here, we're just going to say that the growth coefficient R is K times the effective light intensity. Okay, so that's going to be our growth coefficient for the algae. Yes?
Oh, like a couple slides back, you have like the arrays with the initial concentrations. At the bottom, you have like CO2, 0. And then you use like a variable. Usually variables that like you did use before.
So now we have our growth coefficient, which is what we need. And I'll just say it again with this equation. Say the same thing, just more in equation format. Where here, remember I said I could divide by 24 if I just use my time of day, 1 through 24. Well, I'd put it in here like this, but I don't have it like that in the previous equation. But anyway, I find my I0, or my I at the surface, as my peak I during the day, 800 times the sine curve. Then I find my effective I as I0 times C max minus C over C max. And then I find my growth coefficient R as K times I effective. Well, there's one complication here. Obviously, when our growth coefficient isn't going to vary as the negative sine curve at night. So what we have in our flow chart is if R is less than 0, that's night. So after we calculate our R, if R is less than 0, we go this way, and we just say R is negative 0.1. So our growth coefficient at night is negative 0.1. And then we're going to calculate our concentration in the same way we did before, where we have our concentration at I-1 plus R times C at I minus 1 times dt. And we're going to ignore the harvest at this point, so you won't include the harvest. But during the day, we'll use the same equation. We just have the R equal to the original R. So R, and actually this would say during day, R equals K times I effective. So that's this one. And we're not worrying about the nutrient concentrations now. All we're going to do is calculate the algae cell concentrations, which is C. So C at I minus 1 or C at I equals C at I minus 1 plus DC. And then one thing you can do if you're inputting data from outside, but you want to change something, is you can just comment out the input from outside. So I just changed NT to 24 in my code because I wanted to look at it over the period of 1 day. So here's 1 day. So you should get a graph like this for 1 day. So go ahead and stop the video and try to do the code for the algae cell concentrations based on what I've already told you. Okay, so let's first look at this graph. So what you can see is I have a negative growth coefficient at night. Then I get to about 0.25, right? That's 0.25 of the day. That would be 6 a.m. And then my growth starts increasing because my light starts increasing. And then I get closer to 6 p.m. when my light is decreasing and my growth rate starts decreasing, and then it goes down at night. And actually, there's a big problem with solar angle in algae production because once it gets down, a certain amount, the water just reflects it off the surface. So really, that's why the summer production is so much higher, because the light is directly overhead in midday and it comes up much earlier and goes down much later. So that's why there's a huge difference in production. And maybe you would even close down the raceway, especially in some states like Utah, where it's freezing cold at night. So there's some practical considerations with respect to the sun. Okay, let's look at the code. So what we did is I went to NT plus 1 for I in range 1 to NT plus 1. Then I calculated my time of day as a fraction. Then I put in I calculated my I0, or my I, based on I0 and the sign of time of day. Then I calculated my I effective by adjusting the I based on max concentration. Then I calculated my growth coefficient based on the effective light and the coefficient that I put in there in the spreadsheet. Then I said, if I is less than 0, or it could have said if R is less than 0, then R equals negative 0.1. So that's the only adjustment I need for night. Then I said C at I equals C at I minus 1 plus R times C at I minus 1 times dt. And then I get this curve. So you can see that it's going down at night and going up in the day. And then I have this maximum of about 1.8. And I said my max concentration was 2. So once it gets up close to 2, there's really not much light. And so that's why it stops before 2. Any questions? Okay, so now we're going to add the effect of limited nutrients on the model, or on the growth coefficient. So first we'll look at adjusting the nutrient effect on the growth coefficient, and we're going to assume the Monod model. But this is actually not correct for algae raceways. The Droop model, unfortunately the person was named Droop, accounts for the fact that algae greedily ingest all the available nutrients as quickly as possible and store them in vacuoles in the cell. So there might be no observable nutrients in the water. And this confused us for a long time. The algae was growing and there was no nutrients. And then we looked up and we found the droop model where there's still nutrients. It's just inside the algae cells. They're in these vacuoles, these empty spaces inside the algae. But nevertheless, we're going to assume the Monod model for this exercise, which adjusts the R max. And so R max is based on the sunlight and temperature. And then we're going to add a stress basically. So we're going to adjust R and we're going to move it downward. S represents the term substrates. So all the nutrients are called substrates. And so there might be different stresses. This is one stress, nutrient stress, where you can see that if the nutrients get into the range of the half saturation rate coefficient, the R starts decreasing. As long as the S is much larger than K, then there's really no effect on R. But as soon as the nutrients get close to the half saturation coefficient, rate coefficient, then R is decreased. And again, R max is what you calculate from light and temperature. In our case, it's just light. So now we're going to add the Monod equation to the growth coefficient equation. So we already calculated it, but now we're just going to adjust it downward. And what I've done is I've multiplied the Monod equations for each nutrient. And what's typically done in biological modeling is you multiply all the stresses together. For example, if you had maybe water stress limiting the crop growth by 10%, and also nutrient stress or pest stress limiting the crop growth by 10%, then you would multiply them together to get the total reduction in crop growth. So you'd have 0.9 due to water stress, 0.9 due to nutrient stress, and together the crop would only grow 81%. 0.9 times 0.9 is 80.81. So this is typical practice in biological modeling where you just multiply the stresses together. So we multiply the nitrogen stress, the phosphorus stress, and the carbon dioxide stress together to get the growth rate reduction. So the half saturation rate coefficients for each nutrient are found in laboratory experiments where scientists measure growth rate at different nutrient concentrations. And then they apply the Monod model by regression to the data. And the half saturation rate coefficient is the nutrient concentration at which the growth is half of the maximum. So in these curves, you can see that the growth rate does not change until you get down into the range where the reduction occurs. So that's close to the half saturation rate coefficient. You can also see that different algae species have different responses to nutrient concentrations. So the half saturation rate coefficient is different for different species. Also, you can see that the half saturation rate or the concentrations are measured in micromoles per liter in this case. That's just one way to do it. So in this graph, you can see that the nitrogen concentration N50, that's the half saturation rate coefficient, is set at this position on the graph. Now they have two different types of graph. They're talking about something else, different functional responses. But anyway, you can also see that they're using units of kilograms per liter. And it's easier to use units of moles per liter when we're talking about calculating nutrient concentrations. So these are the half saturation rate coefficients that they reported. For nitrogen, for bacteria and microalgae, they reported 1.8 times 10 to the negative 7th. And for phosphorus, they reported 6.5 times 10 to the negative 8 as the half saturation rate coefficients. Well, I previously found a paper where they reported that the half saturation rate coefficient was 5.4 times 10 to the negative 4th grams per liter, or 3 times 10 to the negative 5th. And that's very close to 1.8 times 10 to the negative 7th. They had kilograms per liter. So that'd be 1.8 times 10 to the negative 4th grams per liter. And so I said that's very close. It's in the same order of magnitude. And the reason I say it's very close is that you normally would not allow your nutrient concentration to get even close to the half saturation rate coefficient. It's like if you were feeding animals, you wouldn't risk them not getting enough food and decreasing their meat or milk production. Okay. So you always operate with what's called replete, or you don't always, but in experiments, they talk about operating with replete nutrients, which means the nutrients never get close to being limiting the growth. So that's why saying it's 5.4 or 1.8 times 10 to the fourth is not a big deal. Now I needed to convert it to moles per liter because I'm going to be calculating my nutrient concentrations in moles per liter. So I'm going to divide, for example, this by the molecular weight of nitrogen, 14. And that's going to give me 0.00003 moles per liter as my half saturation rate coefficient for nitrogen. And then my half saturation rate coefficient for phosphorus is 0.00001 moles per liter. And like I said, I got these values from different papers, not this paper. Okay, so carbon dioxide is more complicated to model because carbon dioxide in the water, which is indistinguishable from carbonic acid, is in equilibrium with carbon dioxide in the air, which would be the headspace over the raceway or over your bioreactor, or it would be air over a raceway. And so we should, if we were accounting for everything, account for this. And this is Henry's law, the diffusion from water to the atmosphere. But we're not going to. And actually, we always ignored this in our algae raceway experiments because in practice, you just inject carbon dioxide into the raceway as a gas and you maintain the concentration based on the pH in the raceway. So you just have a trigger for the injector tied to a pH probe. So we always injected, I think, when the pH reached 6.5, or maybe it was 7.5. So anyway, I don't have any idea how much carbon dioxide was lost to the atmosphere. I don't think it's a really big deal, even considering global warming, because the carbon dioxide that you inject into the raceway is carbon dioxide that was either from the reactor, either from the atmosphere, or is from a power plant or something. So you're taking carbon dioxide out of the atmosphere anyway. Okay. Now in our model, we're going to be assuming an initial carbon dioxide concentration and then letting it decrease. So unlike typical raceway practices, but that's not inconceivable because I think you can add the carbon. I know you can add the carbon dioxide as a solid. I think it might be sodium bicarbonate. And so then you could add it as a solid to your water and then you would have a high carbonate concentration. And carbon dioxide is part of this is all the carbonate equilibrium where we have carbon dioxide, bicarbonate, and carbonate. Okay, so I found this paper with a half saturation rate coefficient for carbon dioxide, and it is in the same range as that for nitrogen and phosphorus. So it's 0.000025. The difference is not the rate at which the growth starts decreasing. The difference is that algae takes up a lot more carbon dioxide than the other nutrients because it's mostly carbon. I don't know if it's mostly carbon, but it's a large part carbon. And so you don't see that in plant nutrients because the carbon is being taken out of the atmosphere. But in algae, the carbon dioxide is being taken out of the culture, just like the nitrogen and phosphorus. So these are our three rate coefficients that we're going to use, half saturation rate coefficients. And then we're going to adjust the R value based on these Monod equations. Okay, the next step in our model is to adjust the nutrient concentrations based on the amount of cell growth that we have. And for daytime growth, we have nutrient uptake. You can see here where this is not night. We have a certain amount of algae growth represented by DC. Then we divide that by grams per mole of algae, and we multiply it times 16 based on the stoichiometric equation for nitrogen. So we have our N0, or our N at I minus 1. Then we have N at I equals N at I minus 1 minus the change in algae concentration divided by the grams per mole of algae times 16 based on the stoichiometric equation, and similar for phosphorus and carbon dioxide. So here's our stoichiometric equation. In modeling of microbial growth, it's typical to have these types of equations where all the numbers refer to moles. That's why we wanted to use moles per liter for our nutrients, even though we're dealing with our algae in grams per mole. So you usually set one value in the cell part of the equation equal to 1. So in this case, we've set phosphorus to 1. And what this means is that there's 106 moles of carbon for every mole of phosphorus. There's 16 moles of nitrogen for every mole of phosphorus, and so on. And then you calculate the nutrient uptake based on the stoichiometric equation, which we will practice with later in the course using, you can imagine it's complicated to set all these coefficients, but we're going to use linear algebra to do it. But you can see the nitrogen is easy because there's only one source of nitrogen, which is nitrate, and there's 16 nitrogen cells in the algae culture. So that one was easy. But the oxygen's complicated. There's 4 equations with oxygen. There's 2 terms. I didn't mean equations. There's 2 terms with carbon and so on. But anyway, this is the stoichiometric equation that we're going to use. And the unit mass of the algae is 3550 grams per mole. So that's not these numbers, but we take the number of carbons times, or the molecular weight of carbon times 106, hydrogen times 263, and so on. So our total grams per mole of algae is 3550. So what we can do is, in order to calculate the amount of nitrate uptake, which is the species that we're going to assume that we have in the raceway, because we add fertilizer as nitrate, we're going to take the cell concentration change in grams per liter. We're going to multiply that times 16. That 16 is over here. And then we're going to divide by 3550. And that's going to give us our change in moles per liter of nitrate. And then we'll do the same thing for all of them. At night, you're not going to remove any nutrients because actually the biomass is decreasing. And I don't think they contribute nutrients back into the raceway when they're decreasing in biomass. This isn't a perfect mass balance if you think about it, but that's how we did it. So in my if statement, if R is less than 0, R is negative 0.1, and you can see that there's no change in nutrient concentration at night. You just set the nutrient concentration at I equal the nutrient concentration at I minus 1. But in the daytime, if it's day, then you do decrease the nutrients according to this equation. So at this point, we'll stop the lecture and let you add your monod equation to your light calculation. So you're just going to adjust the R based on the nutrient concentrations. Those are all in moles per liter. And then you're going to take out nutrients also below, and you have an if-then statement where you have one case for day, which is up here, and then one case for night, which is here. So I'll let you start to work on that. The grams per mole of algae is 3550. Yeah. So the initial nitrate concentration is 0.1 moles per liter. The initial phosphorus concentration is 0.01 moles per liter, and our initial carbon dioxide concentration is 0.2 moles per liter. Now, sometimes the code does not limit the growth rate due to nutrients because they jump across the boundary into the negative range. Because remember we talked about overshooting a few lectures ago? And so that's something you have to be careful of. If your nutrients start going into the negative range and there's no decrease in growth, that means you need to decrease your time step so it doesn't do that. Because you're just, maybe it's above the half saturation rate coefficient one day or one time step, it's below it another. And that's why I say you don't get close to the half saturation rate coefficients. So one thing you could do is increase your nutrient initial concentrations to avoid that. But another thing you could do is decrease your time steps so you do account for the fact that your nutrients are getting close to the half saturation rate coefficient.